Alright everybody, this second video is about graphing rational functions. We already talked about a rational function is one where you have a polynomial over a polynomial. It's not always going to be like the reciprocal ones that we just had in the other video, where it's a number over x plus or minus a number. So it could be a lot more complex where you have quadratics and cubic and etc. So this is where we start to see some really funky functions. You can kind of see some of the examples over here. We'll go through how I created those. But ultimately, we're going to go through kind of the steps. So usually this is called p over q. So the polynomial in the numerator is called a p. The polynomial in the denominator is called q. So the way I think about that is, you may have heard the phrase before, mind your p's and q's. So that's how I think about what this is. So the p's are the numerator function, q is the denominator function. They're both polynomials, and together we make a rational function. Okay. So some key ideas to find x-intercepts of the graph. We're going to set p equal to 0. So the p function, the numerator, you're going to set that equal to 0, solve for x. So that might mean you have to factor. Okay. To find the vertical asymptotes, we talked about this in the other video as well. You're going to set your denominator, or q, equal to 0 and solve for x. That could involve some factoring first. Okay. And then horizontal asymptotes. We were working with option 2 in the last video, where the degree of the numerator was less than the degree of the denominator, because the degree of the numerator in the last ones were always 0. The degree of the denominator in the reciprocal functions was always a 1. So we had this unless it got shifted up or down. Okay, so now we're going to add case 1 and case 3. If the numerator degree is higher than that of the denominator, to find the horizontal asymptote, you want to factor first and cancel out any common factors. And then you're going to divide the numerator by the denominator. Okay, so that usually ends up with what we call a slant asymptote. Okay, 3 is probably the easiest one. If the degrees match, we take the leading coefficient. That's what LC stands for. Leading coefficient of the numerator over the leading coefficient of the denominator. Okay, and then we have to watch out for this idea called a whole. So if we see a common factor in numerator and in denominator, then we are going to see that it is a whole in the graph. Okay, so just something to think about. Okay, so we're going to go through a couple of the examples here. I want to make sure I have a pen ready. Awesome. Okay, so in this first example, you can kind of see we've got case 1. Okay, numerator degree greater than the degree of the denominator. So first thing I'm going to do is I'm going to factor anything that I can. The numerator I can factor into x plus 3 times x minus 3 because it's a difference of squares. They don't have any common factors. Okay, next thing I do is I set my numerator equal to 0, solve for x. That's going to give me x-intercepts. So I know my x-intercepts are at 3 and negative 3. Okay, and then there shouldn't be any holes because I don't have any common factors in numerator and denominator. Okay. Vertical asymptote, set my denominator equal to 0, solve for x. That should happen at x equals negative 2, which means my domain then is that x cannot equal negative 2. Alright, horizontal asymptote. Now to get this, like I said, this is where we do division. So I did synthetic division. I put negative 2 in the box, and then I did 1, 0, negative 9. Some of that's kind of off the screen, sorry about that. But I start by bringing the 1 down, multiply by what's in the box. This should be a negative 2 right here. Okay, add 0 minus 2 is negative 2, times a negative 2, fill the next spot is a 4, negative 9 plus 4 is negative 5. So this is the thing though, when you're finding this dividing p over q, you don't care about the remainder. So what we do care about though is this is my constant, and then this is my x. Okay, So what we have then, the horizontal asymptote, is y equals x minus 2. And that's this blue line right here. And you can kind of see that both of the red branches follow along that line. So what does that mean about the range? The range is going to be all real numbers. So I could say negative infinity to positive infinity, or all reals. That probably would have been easier for me to do instead of writing it like this, but that's okay. All right, second example. I'm going to factor first, and then what you should see is we've got a common factor here, right? That x plus 1. So those are going to actually cancel each other out. Okay? So when we find our x-intercept, we're only going to use the factor that is left, that's not repeated, to solve for x, so we get x equals 5. The whole is going to occur where those repeated factors are. So at x equals negative 1, because I set the factor equal to 0, solve for x. So what that means is on the graph where I have negative 1, it's kind of hard to see, but there's going to be a hole in the graph. Okay? Vertical asymptote, we only set the denominator left equal to 0 because a hole is kind of an asymptote. So if you said 1 and negative 1 here, I technically wouldn't count it against you. Negative 1 really isn't the asymptote, it's a hole though, so I'm going to write them separately, but we need to keep track of both of them for the domain. We're going to say the domain is that x cannot be negative 1 because it's a hole, and then positive 1 because that's the asymptote. So again, if you're looking at the denominator, it's going to tell you the values that x cannot be, because if those values are plugged in, we have a 0 in the denominator. Okay, horizontal asymptote for this one is easier because we're working with case 3. Degree on top and bottom are the same. The leading coefficient of each is a 1. So I'm just going to take 1 over 1, which is 1. Okay, that's the only value then for the range that we would say y cannot equal 0. I like to put those in with dashed lines. And then again, I went to the calculator and got a couple key points, one of them being at negative 1. If you trace this and you say negative 1 in there, we're going to see a hole. So I'm going to pause for a minute and I'm going to get that plugged in the calculator so that you and I can both take a look at it as well. Alright, I'm going to be plugging this in my calculator, and to make it easier, I'm going to go second y, oh shoot, nope, it's not that one, it's alpha y equals, there we go. And I want to pick option 1. So again, I did alpha y equals, and that gave me the fraction menu. I want to pick option 1. Okay, so then it actually gives me a fraction. It's a lot easier to do it that way. You don't have to. No, I don't want to hit store. Whatever. X squared minus 4x minus 5. And then I can jump down to the denominator and have x squared minus 1. Okay, now, could you do this without that little trick that I showed you? Again, to get there, you go alpha y equals, okay? If you don't want to do that, then that's fine. What you can do instead is you would just have to have parentheses and put the top part in the parentheses, right? So you do your x squared minus 4x minus 5, close parentheses, divide. Oops, I have a double parentheses for some. Oh no, I didn't mean to clear all that out. Shoot. Try again. X squared minus 4x minus 5, close parentheses, divided by, parentheses again. Okay, x squared minus 1. So either way, okay, if you type it in like how I did in Y1 or in Y2, we're going to see the same thing. So I'm just going to make sure it's zoom 6. Okay, so they're the same graph either way, whether you use that little alpha y equals fraction trick or not. And then we trace. A couple key points I would look for is a y-intercept. That's always helpful to find. The other one we wanted to look at was at negative 1. Okay, you should see there's not a y value. Okay, that's because there's a little tiny hole in the graph. You can hardly see it if you're looking on a graphing calculator, and you definitely can't see it for sure on the graphing calculator. Desmos can kind of show it to you if you're looking very, very closely and hover over it perfectly, then it'll show you that it's a little just open circle right there is what we're going to put on our graph. Okay, and then if you want, you can plug in some other values. That's not a great point to have, but -3,2 is a good point to have. We can also check on my intercept here. I think we said it was at 5, so I can check and make sure that we're right on that, and it does look like we are. So the key on this one is going to be to make sure that you are checking yourself with Desmos or a graphing calculator to get some more points. Okay, so again, we're kind of just going through. Rational functions are a ratio of polynomial functions. First thing you always want to do is simplify. Find x-intercepts by setting the numerator equal to 0. Find vertical asymptotes by setting the denominator equal to 0. And then you find the horizontal asymptote using the rules below. Case 2 is what we used in reciprocals. 1 and 3 are a little bit different. So division of p over q without the remainder. If p is greater than q in degree. If the degrees are equal in the numerator and the denominator, then we take the leading coefficient of each one. Okay, and then we identify the wholes. So this is a great little step process to have. If we were in class, like I said, I'd focus a lot more on not using the calculator and looking at what we could do without it to find out some more information. But for now, all I want you to kind of be able to do is factor, find your x-intercepts in the numerator, factor the denominator, find your vertical asymptote, and then figure out what case it is to find the horizontal asymptote. So I told you that there was a reason that we were doing division, and it comes down to this type of stuff, okay? And then wholes, again, are repeated factors in the numerator and denominator that we get to cancel out. Okay, so I'm going to go through a couple of the examples. I will have the completed notes that have all of this stuff in. Okay, so remember for x-intercept we set our numerator equal to 0, or you can plug in 0 for y and solve. Okay, vertical asymptote, we're going to set our denominator equal to 0, and then this is case 3. Okay, leading coefficient divided by leading coefficient. So I set all those things up. Remember, vertical asymptote ties into the domain, horizontal asymptote ties into the range. There's no repeating factors, so there's no holes in this. Okay, and then you can jump to the calculator, just verify and make sure you're on the right track with what you're thinking about the x-intercept and the vertical asymptote. Okay, so it should look like each branch is kind of approaching x equals -4, and then also the line y equals 1. Okay, on the next page, I want you to be able to go through and determine, that's my, I want you to go through, if you're looking with me on the notes, I want you to be able to go through and determine what each of the cases are. So go ahead and pause the video and do that right now. So decide if it's case 1, case 2, or case 3. Pause the video and try that out. Okay, and then I'm going to kind of go through. So it should be case 3, then 1, then 2, then 3. For each of these, you can pause the video now and make sure you're seeing what I'm seeing for intercepts and asymptotes and holes and domain and range. Okay, so I'll let you kind of look through those. But again, set your numerator equal to 0, find your intercepts for each of these. Okay, this one, for number 4, it has a hole. Number 3, it has a hole. So you cross those out early on, and I had started writing it already for number 4, so I just crossed it out. It doesn't have an x-intercept because it's the same as the hole. Okay. Number 3, we do have an x-intercept, and then we have a hole at x equals 1. Okay. So you could technically say that x equals 1 is a vertical asymptote, or you could just say none here as well. You could say or none. Okay. So kind of go through these, take a look, make sure they make sense. Then on the next page, I want you to go through and see if you can identify what are the cases, and then you'll have to check back with the completed notes to make sure you got them right. Okay? Here's the cases I have, 1, 2, 3, and 1. And again, check the completed notes. Let me know what questions there are, but use your calculator.